All right, here's a few things. So this is kind of cute. They found a way to totally stop malaria by protecting the mosquitoes. The mosquitoes get infected with malaria and then they pass it on, and they have found a fungus which can prevent mosquitoes from becoming infected. So all they have to do is to infect the mosquitoes with the fungus, which is apparently harmless, to prevent the spread of malaria. So that sounds pretty interesting. Rachel Toback, who is a social engineering expert, is giving a free talk tomorrow. So you might look at that. It looks like it's 9 in the morning here, but that's a good thing. She won the social engineering contest, and she has very fun, very professional looking talks. So you should check it out. She's the real expert in social engineering, helping companies change their policies so you can't lie to people so easily over the phone and trick them into doing the wrong thing. Elon Musk, who seems to be very, very crazy lately, although he's gone through spasms like this before. He sold his house, he had a baby, he gave his new baby an unpronounceable, unprintable, crazy name, and now he restarted the factory. The state of California has approved opening certain factories that would include his, but his county has refused to let him open the factory, so he just opened it anyway and said, I'm going to be on the line, and if you're going to arrest anybody, just me. And I don't think the authorities have decided yet whether they're going to arrest him or fine him or what. But it's a big issue. He wants to open his factory, and he's a pretty demanding guy. Anyway, so I'll move this over here. All right. So this is an interesting thread about app privacy, and I'd like to make it bigger. There we are. I was unaware of this, but it makes a lot of sense. If you build an app could be a very simple thing on your phone that just gets data from, say, one source by a simple protocol. But in fact, almost every app is involving a web browser and loading web type pages over web servers. And what that means is you can inject HTML into almost every app, and therefore you can inject image tags in the app, and it will render the image tags and fetch other data from other servers, so you can cause an app to load content and send traffic to arbitrary servers. So it's an interesting issue, because here's the attack. You some way find some untrusted input that goes into the app, then you put in things like image tags, and that compromises your privacy. This is how they caught the people that were hiding behind Tor, the pedophiles, because if I can trick you into loading an image from my server, then I have a record on my server of your IP address. So for medical sensitive apps like COVID tracing apps, this is bad. And it's another example. The security level of an ordinary app is not good enough for voting, and it's not really good enough for medical devices either. Let me figure out how to mute the noisy people. Ah, here it is. Okay, good. I have 20 screens. Anyway, so yeah, and I see Ed says, yeah, Elon Musk has been a controversial figure, yeah, but his company makes a lot of money. And so Zodino Kobe is the #1 ransomware. I've been hearing about this for a year, and it used to have a problem that it could not encrypt your open files. So it would try to kill services to reach the files, but now it has found the Microsoft API call just for this purpose. I remember this was a big issue years and years ago when I was a server administrator. We had a network, and I had to always run around and turn off all the machines before I could restart the database server, because otherwise it would lock files. And to get around that, Microsoft made various calls to change files while they're open. And Microsoft's API is called the Restart Manager, because this is another big issue. You have to keep restarting Windows machines when they put on updates, when you put on patches. And the reason it does that is to unlock the files so it can change it. So Microsoft made an API call that will close a process just to let one file be unlocked, which is how Linux does it. Anyway, so this ransomware now does that too. And their decryptor does it also. So your decryptor can decrypt files even while they're in use, because it will stop the process as needed to make that possible. This one got a lot of attention. Thunderbolt is just a fast USB-like port to move data in and out of machines. I hear about it mostly on Macs, but apparently a lot of PCs have it too now. And in order to make it faster, they gave it direct memory access. So that port can directly read and write from RAM. And it turns out that you can use that to undo all encryption. Even a machine that has hard drive encryption turned on, you can steal the data from it and unlock it through the Thunderbolt port. And this cannot be patched without a hardware redesign. So apparently this applies to many, many systems, including some that are completely up to date. So people are all freaking out about it. And there are some systems that never put on the Thunderbolt port and are therefore not vulnerable. Almost everybody with a Thunderbolt port is apparently vulnerable. And Thunderbolt is going to be integrated into USB 4. So people are concerned that when USB 4 comes out, they should make sure that it does not duplicate this flaw. Of course, that only applies if they get physical access to your machine, but it would be good for cops that are trying to get data off machines and so on. Anyway, so there's a video about Wireshark, but I think we'll just move on to the official stuff here. So this is the last class, and I've got a lecture as usual tonight, which is not normal for my last class, but the schedule has been a little disrupted this year by all the emergencies. So I'll finish the last bit of chapter 7 and do chapter 8. And then I've got at least one person that wants to give a presentation. If anybody else wants to give a presentation, let me know. My grader is working on the papers that have been coming in, and I'm going to write instructions next time to make it more clear what I expect and to explain to people how to get Grammarly. Grammarly is very good. It's far better than the grammar and spelling checker you'll get with a Microsoft Word or something. So in the future, I'm going to tell everybody to make sure and run your stuff through Grammarly. Anyway, because you can get a free version by putting a browser extension in. Anyway, let's talk about the last bit of chapter 7 and chapter 8. Let me get to here, and here it is. Okay, come on, get big. All right, fine. There, now it got big. All right, so I got backups and availability, just something we covered a little bit earlier, but a little more detail here. If I can get my computer to cooperate. So to decide what you need to have, you need to figure out what tolerable downtime you can have. And more people want continuous availability, which means a maximum tolerable downtime of 0. You'd really like to have your stuff just stay up all the time, even when there are problems. So that's where we're headed. One option, of course, is hard copy. Printing things out on paper is one possible way to make a backup. Of course, it's a drag because you have to retype it in or scan it, but some people consider that. Anyway, backups, the most common type is a full backup. You back up all the data on a server. You can also do incremental backup, where you get all data changed since the last backup with these little increments, or a differential backup, which is the one in between, where you refer the backup to the last full backup, so you never have to play more than 2 tapes to reconstruct any day in the past. The only reason you'd ever use any of those second ones is if your machines are so slow or something, or you have so much data that it's too expensive to back it up full every night, if your backup period is 1 day. Anyway, so you often have a series of tapes or other storage devices that you're rotating in. And so you have, you rotate them for 14 days, and then you take 1 tape each week and archive it for longer, and 1 tape each month and archive it for longer, so that without having to pay for too many storage tapes, you can have a record of the past, although you don't have a copy of every day all the way into the past. Electronic vaulting is another option. Instead of having you run your own hardware devices to make all these backups, you can just do it in the cloud with something like Iron Mountain. You subscribe to some service and you send your backups up there. All right, you can use remote journaling, which will save database checkpoints periodically throughout the day, or database shadowing, where you just have 2 identical databases that are completely synchronized all the time. And that, of course, is the most expensive, but the fastest recovery. High availability clusters are not backups. Backups are disaster recovery methods. In case your building burns down and everything is destroyed, you use backup to recover. A high availability cluster just prevents faults, like the failure of one hard drive or the failure of one server, from causing an interruption in service. So active-active are where both systems are working all the time, and that's load balancing. Active-passive has a backup system that keeps an accurate record of all the data, but is not used until the first one fails, and then it fails over. One issue is that you might buy proprietary software from a company, which then goes out of business. There has been a law passed that says that if you have purchased software from someone and they are no longer available to support it, you are legally allowed to reverse engineer it and hack into it to maintain it. But if another way to do this more in an organized way is to arrange before the company goes broke to have a copy of the software source code somewhere in ESCO, so it would be available to the customers. I don't hear of this happening too often. What I hear far more often is consumer devices that people buy and then the company goes broke and your devices just quit working. This is happening to a lot of cloud-based services. All right, and so you got to test your plan. You can have a review of the plan where you just read through it to try to find flaws. You can have a read through, which is a little more detailed, or a table talk walkthrough where you have representatives of people there looking through everything. Then you have teams actually carrying out the process, parallel processes, or complete business interruption, the most powerful test where you actually turn off servers or something during a working day. This is what Netflix does. Netflix has a thing called the Chaos Monkey that deliberately turns things off randomly throughout the day so that everybody is constantly forced to think about backups and high availability. And the end result is their stuff is very reliable. So you train people, they have to know what to do, how to start the power, who they should call. Everybody should be aware of their role in the plan, like how they find out whether it's safe to go to work. And you have to maintain the plan. You should have a change management plan, and your disaster recovery team and continuous availability team has to be part of that so they know what's happening. There has to be a version control of it so you know as you're updating your plan. And so here's common mistakes. The one you hear all the time in every part of the CISSP is that if upper management doesn't support you, you're in deep trouble. You have to have upper management motivating people to invest resources all through the company to keep this going, and you have to test it and keep it updated. This is a common mistake. All right. And so there are frameworks for this stuff. There's a US government framework from NIST. There's an international framework from ISO, a British standard, and another international standard. And you would, if you're going to be a big company dealing with government customers, then you'd want to meet these standards. So here's the Business Continuity Institute with this plan here, business continuity, implementation, and validation of it all. So let's take a look at the Kahoots for here, which I should have someplace back here. All right, somehow it's not available. Let's see what's going on here. Windows, there they are. Okay, that's screwy, probably from something being full screen. Anyway, this was 7E. All right. All right. All right, I think 7 is the maximum possible. Oh, good. Well, then we will go. All right, what system has an MTD of 0? Continuous availability. All right. What system has 2 identical copies of a database? That's shadowing. All right. What DRP test is the most dangerous? Okay, obviously, business interruption. All right, and which one of these is not a common error? Okay, excessive testing would be it. So you've got Erica, I guess. Blue will have to tell me who they are if they want points. All right, and I don't know what's going on with Erica. It looks like none of those people are getting points unless they explain who they are. Anyway. All right. Anyway, aha, I see a clue. All right. Now I found out who Blue is. Okay. All right. So I got one person's name anyway. All right. And let's go on to the next chapter. Aha, I see another name. Okay, good. And I now know who real Erica is. All right. And aha, okay, good. Now I know them all. Good, thank you. All right, good. So let me go here. And chapter 8 is good. Let's do that. All right. Come on. Okay. Fine. All right. So software development. Your first basic concepts. The only thing your computer ever runs is binary machine code, which is just raw bits. You can express them as hexadecimal, but nobody much wants to write at that level. So they write source code in languages like C and Java and Python. And it is compiled down to assembly language or interpreted when it runs. It runs machine code. Assembly language is an attempt to write machine code readable by humans with commands like add and subtract and push. Compilers translate source code into machine code. Interpreters translate one line at a time into machine code while the program runs. And bytecode is an intermediary form of machine code which is not tied to hardware. It's tied to a virtual machine, like a Java virtual machine. So you can write code in Java and compile it into bytecode, which can then run on any hardware because it runs in a Java virtual machine. So it runs a little slower, but it is platform independent, which saves a ton of money in development. You don't need to develop a separate version of your software. It'll run equally badly on all hardware. So procedural languages like Fortran introduce procedures and functions and subroutines, and then object-oriented languages for the next level of abstraction where you can define an object like an employee that has methods that are like subroutines and data stored in that object, and then you can have more objects created based on the object that inherit properties from the parent object, and that's the way almost all coding is done these days, C++ and Ruby and Python and so on. So here's the Metasploit source code, which is in Ruby, and so it defines a class Metasploit exploit, and then it includes the HTTP client and the file dropper and defines it down here. And this is all object-oriented code, how you tie modules together so they work together. And now there are fourth generation programming languages coming out that will automate the creation of code. Modern programming tools are integrating artificial intelligence to suggest code to you the way automatic spelling checkers try to correct your spelling as you type, and so it goes. All right. So computer-aided software engineering is the plan here. There are tools that will support the task, workbenches or environments, and 4GL, these advanced techniques to try to make programmers more efficient. So there's two ways to do it, top-down or bottom-up. Top-down is where you start by defining the job you want to accomplish, and then you write the functions to do it. Bottom-up starts with low-level implementation details. All right, and that's the more common way to do it with object-oriented languages. So you can make closed source software like Microsoft Windows and Microsoft Office, where the source code is a business secret. You can't get it, and it would be considered a huge blow to the company if it leaked. Or you can have open source, like Linux, where everybody publishes the source code so anybody can modify it. Both kinds can be free or have limitations on the use of them or charge money. So you can have public domain, free to use, proprietary stuff that's copyrighted or patented. You have an end user license agreement you agree to when you install stuff. And there are a whole series of open source licenses where even though the software is available, there are restrictions saying you must always include the software with further copies, or you must always, you can never charge money for it, or that sort of thing. And there are development methods. The early development method was a waterfall where you just define the requirements in systems, software, then you analyze it, design the program, code it, test it, and then send it off into operations. And you just imagine like an assembly line to build a car, that you just go through one series of all this and you're done. This was the original idea, that the same kind of stuff you did to build hardware you could use for software, but that turned out to be very unrealistic because you keep on having problems at one level that require you to go back and redo step at an earlier level. So the next one is to have some kickback, where a problem here at testing causes us to kick it back to be fixed there. So you have one way to do it. Then there's this Ashimi model where the steps overlap to try to more efficiently handle that kicking back process. And there are many other ways to do it. Agile is one that's quite popular, where you have this plan to have teams of people working together with a lot of collaboration to try to prevent wasting a lot of time redoing work because problems show up later. Scrum is another way where you do one team does all the steps all the way through, so you don't have so many misunderstandings, or one team does not understand what the previous team was planning to do, so they create a problem which causes you to have to go redo work and slow down the product and waste money. Then there's extreme programming, where you have two people constantly working together for pairs of programming. There's many shops, each with different plans here. There's a ton of software being written, and it's quite expensive to make, and it's expensive to constantly update, and they're trying many techniques to make it faster and cheaper. Then there's spiral, where you don't imagine sort of that you're ever done. You make a prototype, risk analysis, then you can make your consequences, then you make another version of it, risk analysis, and another version, and you just go around in many cycles this way. Another way to look at it. All right, then there's rapid application development, where you make dummy products just to get what you need up very quickly. And there's rapid prototyping. This is essentially the code I write. I write very simple things that work just for my classes, and they don't really scale or anything. This is quite common. This is what academics usually do, is just proof of concept coding. They invent a new encryption scheme. They write a very simple program that will do it enough to prove that it works, but you can't really implement that code in production. It doesn't scale to volume and all that. So there's development life cycle, which is pioneered by Microsoft to try to deal with the problem that you have these problem reports and attacks and bugs coming in all the time, and you constantly need to patch code. So Microsoft developed this software development lifecycle. It's also a government standard now, to try to make sure that security is included in every step, and you can hopefully keep your product patched as you have to. So you make a security plan, you have a sensitivity assessment to define how important different parts of it are, then you determine your security requirements, and you implement it. And you plan right from the start to have testing and some kind of accreditation to show that it does obey your standards. So you got maintenance, audits and monitoring, and then a plan to dispose of things and sanitize them when you dispose of them so you don't leak source code or other secrets. All right, you can have a product team that focuses on what the customer needs, the entire life cycle. And we mentioned before, you have software escrow. You might have to put your source code someplace so your customer can audit it or have some degree of access to it if necessary. Their code repositories and version control are a huge issue these days. People use GitHub and Circle CI and related products, and you have to have your source code available to all the team, which is scattered all over the earth, and yet you don't want it to leak to the whole world. Some big company had their private repositories hacked into just last week. forgotten who it was. One of the major, might have been Microsoft. The private repositories were leaked out. Many developers do in fact put API keys and encryption keys and passwords and stuff in the source code, so it's really quite dangerous if that source code leaks out. All right, your APIs use the service, and there are a lot of web attacks on APIs, so you can send malformed requests to them. This is how a lot of APIs intended for cell phones end up leaking data, because you can send the requests and get at data that's not properly secured. So there's an API toolkit, and there's an OWASP top 10 vulnerabilities for API, and it's very much like web applications. There are all these considerations you have to put into it to make sure that your API is not vulnerable. So your software has change management. So if you want to make changes, then you have a change management plan, a control board, you identify the things you're changing, and you monitor the consequences. Another big issue these days is DevOps. It used to be that you'd have large portions of your company that are non-technical. They might know only one thing, but if they need a server, they have to go to IT. And so you have an IT team that doesn't really understand what the other party team needs, and usually have a huge backup at IT of requests that they can't really handle. And you have a bunch of company where they can't do something, you have to wait for the IT team to do it. So the new DevOps system is everybody should be technical, and everybody should be building the systems they need to get their work done and automating their job. It's a whole new system, and there's a very good book about it called the Phoenix Project that I highly recommend, that explains what DevOps is. Amazon is the king of DevOps. Amazon has 144,000 new rollouts of versions per day. So their product is constantly changing, like every few seconds, so they can change dynamically to very rapidly to meet customer demands. And that is considered a huge improvement over the old system, where you'd have versions and wait for teams to develop the next version all the time. So we're up to 8A. All right. And so 7 people. All right. There might be one more coming. I'll give them a few seconds. I guess not. All right. So what's the computer code closest to English? Okay, that's the source code. All right. All right, what method uses the same team for every step? It's a Scrum. I think a term that came from rugby. All right, what method uses prototypes and dummy graphic user interfaces? That's rapid application developing, rapid prototyping. All right, and what category is GitHub in? Okay, it's a code repository. All right, so there we are. So JZ, I think that's a real name, real initials. Yellow will have to tell me who they are. Stephen. All right, Stephen is one last time in Sat. Do I know who that is? All right, and I see who yellow is. All right, good. Fair enough. All right. So I got those scores. Good. Get rid of this. And back to here. Okay. So databases. It is a structured pile of data, And so you can have queries that search the data, you can insert records, you can delete records, and you have a database management system that manages all this. So a database administrator is the highly privileged account that can change things like the structure of the database. The most common type is structured query language, SQL type databases. They're used for banking and many, many other purposes. So there are some attacks. If you have low privilege data in the database and high privilege data, you can use an inference attack to just examine all the low privilege data and try to deduce what's missing, and that must be the high privilege data, or an aggregation attack, which is very much the same thing. Both of these involve looking at low privilege data and deducing information about high privilege. Relational databases, hierarchical, object-oriented, and flat file are types of databases. The most common is the relational database. An RDBMS, Relational Database Management System, is the most common, like SQL. So you have a table with things like username and as admin, and then another table called social security number that has names and social security numbers. And these two tables are related, and that's the relational database. It knows that this username should match that username. This is the most common type of database. So you have rows, which are called records, and columns, which are called fields, and you have a primary key, which is the unique identifier of an entity, like a customer or an employee, something like a social security number. And you join two tables by connecting the key in one table with the key in the other table. You have referential integrity, which makes sure that the table doesn't have a contradiction. So there cannot be two employees with the same social security number or two products with the same product ID number. You have semantic integrity, so fields cannot be the wrong type. You can't put letters in a numerical field. And you have a requirement that everything has to have a primary key and the value cannot be empty. So you can always use that value to find things. So here's a table lacking integrity. Here's two entries of the same social security number, and that is forbidden. When you try to enter the next one with the same social security number, you'll get an error saying you have violated referential integrity and you can't enter that data here. Database normalization removes redundant data from databases to make sure there's only one copy of it, so you don't get inconsistent records if you do something like update a name or an address and you don't get all the copies of that name and address. Database views are things like point of sale devices where you're seeing just a little bit of information in the database, or your profile page on something like Twitter where you're seeing data in a database, but you're only seeing the records that apply to you or the records that apply to the current transaction. Data dictionary describes the tables, and a database schema describes the attributes and properties of all the tables. So here's a simple database schema. You have an employee table that has these attributes and they have rules. This one is digits, this one is a string. Then you have an HR table with these fields, and that whole mesh is called the schema, the layout of the table and the types of data stored in every record, in every field. So you can have languages to perform queries, data definition languages, data manipulation languages. The most common one used is SQL, structured query languages. There are many different versions of SQL. Oracle uses a version, MySQL is the open source, Microsoft uses ANSI SQL. They're very similar, but they're slightly different in how they work in detail. So you create a table, you can delete a record or a whole table, you can insert a record or change a record, or you can select to just find data in there. So here's the one you see a lot, select star from employees, or title equals detective is one way to do it. So then there are hierarchical databases like the DNS, which is a distributed hierarchical database. There are many servers, each of which have part of the data. There are root servers that only have 13 records telling you where the top level servers are. The top level servers know where the start of every company is. So they've got a really big record. They would know where the head of google.com is, but if you want support.google.com, you'd have to ask this server where it is. So it might take several queries of different servers to bubble your way through this and find the information you're looking for. Object-oriented databases are like object-oriented programming. They store objects, which are a more abstract quantity than just a record. And you have database integrity. An unauthorized user might change or read the data in the database. And so if they try to commit an update, then you might have a problem. You might even have two authorized users that try to update the same table at the same time and have a collision. So the database management system should resolve that and roll back one of the changes and give them an error message so that you don't create a damaged database. You take either one change or the other, and you make sure that the other doesn't happen, and the administrator is informed that their change has failed. So there are highly available databases, like all other server objects with many servers. There are replication systems that copy the contents of the database, and shadow databases, just like other servers. Data warehouses are huge collections of data. Like Google has a monstrous one, which has the top, used to be 2,000 characters out of every web page, something like that. And there's data mining, which is the big business of hunting through a vast pile of data like the internet to find things like credit card fraud or customers that might want to buy your product or lots of things. So there's object-oriented design and programming. This is using an object-oriented language like Java or C++. You have an object, and the internal structure of an object is not visible from the outside. You can have commands that just manipulate the entire object and you don't see inside it. That's called encapsulation. So you have objects, and inside the objects you have methods, which are active code that can do something to an object. And then you have messages that communicate between objects. You can have inheritance, where you have a new object created based on a previous one. So it inherits properties from the one above it. And we'll talk about these others down here. So here is a method. You have an object that can perform something called addition. So you could input a message of 1 + 2, and the output message is 3. So you can have delegation. If you go to Addy and you send it a subtraction message, instead of just failing to do it, it could know that if I get a message like that, I'll send it over to Subby, who can do the subtraction. And you can have another, your Addy can have polymorphism, where it can add numbers, and it can also add strings, where it just concatenates them. So it has more than one actual function, and it looks at the nature of the input to choose which function is in fact performed. And you can have polyinstantiation. This is where you'd have 2 requests for the object from the same input. And if you come with top secret privileges, you get one answer, but if you come with secret privileges, you get a different answer. This means there are multiple records at different clearance levels. There are object request brokers that sit in the middle, connecting systems together, like Corba and COM and DCOM are this. And this is Microsoft's system, which allows you to write code which takes requests from other code and have that code reused in a different context. So .NET is Microsoft's update to this system. And Corba is an open source version of the same thing. We have an interface definition language. So you provide a software object that can take inputs, and you just specify the inputs, sort of like the Facebook API. They just tell you, give us input in this format, and we'll process it. All right, so you got object-oriented analysis and object-oriented design are systems used to prepare these. And so you'll have packets coming in with PCAP, and then you'll have an analysis object taking in this data, passing it through different systems, and then sending it to various alerting objects. So a network intrusion detection system could be built in an object-oriented fashion. All right, this must be B, which is here. Okay. All right. All right. Okay, that's everybody. Okay, what database uses joins to connect tables? That's the relational database. The join is the connection between the tables. All right, what process removes redundant data? Normalization. All right. What concept is also called data hiding? All right, encapsulation. And which one is open source and vendor neutral? Arba, good. The other three are all Microsoft and proprietary. All right, so we got Jesh and Vu. Steven. All right. So we're down to the last section, which is here. All right. So measuring the effectiveness of your software security. There are tons of bugs, tons of errors, and so many vulnerabilities. People put hard-coded passwords and credentials. There's buffer overflows, SQL injection, path traversal, remote file inclusion, many errors, which we cover in all our other courses. So buffer overruns are a consequence of C. If you define room for 20 characters in C, C doesn't really remember that and implement it very well. It just remembers where it starts, and it's up to the programmer to not put more than 20 characters in there. So that leads to memory corruption and remote code execution in the worst cases. There's race conditions where your program will store data someplace and then come back and read it later and use it without considering that some other process on the machine might have changed that object in the meantime. And that creates these race conditions where there's a brief instant of vulnerability when you can get away with something you shouldn't be able to do. Cross-site scripting is where you have data that is supposed to just be static data, but you insert active code into it, and that code runs on the machines of people that view that web page, is where it's typically done. The browser exploitation framework is an older security product used to demonstrate this. Cross-site request forgery is where you trick a user into performing an unintended action. So they click on a URL thinking they're just going to see a web page, but it has an unexpected effect like performing a money transfer or purchasing a product. Privilege escalation is where you move to a higher privilege account like administrator or domain administrator. And horizontal escalation is where you move into another user's account with the same level of privilege. And of course, both of those are violations of security policy. Backdoors, like rootkits are a common type, is a permanent ownership of a system where there is some secret way in that's unauthorized. And this turned out to be quite commonly done by developers. A lot of people have secret administrator passwords in their product. Cisco has announced at least 8 of these in the last year, that their products have hidden, unchangeable, hard-coded backdoors in them. Apparently, they really had a policy of doing this, and they haven't managed to train their whole development team to knock it off. So when you find something, you can do full disclosure where you just dump it all publicly on a blog, but then people will get mad at you, and not in America, but in other nations, you might even be guilty of a crime. There's responsible disclosure is considered better these days, where you tell the vendor privately and give them some time to patch it before you dump it publicly. The capability maturity model is one way to develop quality software from Carnegie Mellon. And so you have levels of maturity, and all your security plans go through these levels. Nobody is perfect at security, and it takes years to get more better. So you start by just writing software without any real plan of security. Then you have some kind of project management where you at least organize things so you can repeat your process. Then you document your process, manage your process, and the top is always optimizing, where you specify your goal, you make controlled, organized steps to achieve your goal, you measure how good the results are, and then you improve your process to achieve your goal better. All right. So you can go to software testing boards, and they will decide various levels of success, whether it's good enough that the users think it's good enough, or whether it meets other levels up to compliance with standards. So there's commercial off-the-shelf software. This is when you buy stuff, you have to test it to see if it works to do what you think it should do. And you might pay people to custom design software for you, and then you'll have a service level agreement explaining what they're promising and what the punishments are if they don't do it. And then everything is full of artificial intelligence now, machine learning. It's a big buzzword. It's getting more and more powerful. So you've got a knowledge base which contains rules that the expert system is used, and then it has an inference engine that follows the tree. So you have, you can also have a neural network where they have a bunch of nodes with connections, and it changes from experience, so it learns the way a human learns from experience. You can also use Bayesian filtering, a very rudimentary system where you just look for keywords. This is what simple email spam filters use, and that's why they misspell words in spam emails to get past this kind of filter. So you can have genetic algorithms where you have a whole series of random computer programs, and they can combine to have offspring, and they can somehow compete and kill off the less successful ones so that they evolve. This is one of the many ways to make self-learning systems. All right. So we're up to the last one, which is HC. Oh, good. I see a name here. Good. Yeah, for the initials, I thought that was it. All right. Good. All right, I'll give it a few more seconds. I guess that's it. All right. What flaw does PHP have? Local file inclusion and remote file inclusion are the most common ones. PHP is involved in SQL injection, but it's not really a flaw in PHP. All right. I know what you're thinking of there, though. All right. What flaw is also called a race condition? All right. Time of check, time of use. I'm thinking SQL injection is not that bad an answer for the previous one, but I can't change it. And it's in the spirit of the unfairness of the CISSP exam. You could argue that. Anyway, all right. And what's the problem caused by developers leaving test code in a production product? That's the backdoors. I think this is what's going on at Cisco. All right, and the software quality framework from Carnegie Mellon. All right, that's the capability maturity model. All right, so, foo, all right. And that's Ed, I reckon. First time I've seen Ed here, actually. And Stephen, all right, good. So I've got all those scores. All right. And some people may wish to give presentations. The only one I know is Ed, who emailed me something. If anybody else wants to present something, let me know. But in the meantime, I'm just going to play this video that Ed sent me, which I've got here in another window. So let's take a look at this.
Greetings from quarantine. Today, I'll be talking to you about Layer 8, going beyond the OSI model. Now, in the last presentation, I outlined the steps that we've taken at the San Francisco Housing Authority's security posture, which covered the gamut from cyberspace all the way to the endpoint, making a point to name drop Layer 8, which, if you haven't guessed by now, is the end user. It's the unofficial Layer 8. Now, a worker likes to be able to just bring their own IoT devices to work and connect them to the network. You know,